What if everything you thought you knew about the universe was just the tip of the cosmic iceberg? Picture a reality where the fabric of space and time isn't just a static stage but a living, breathing entity, where black holes aren't just cosmic vacuums but portals to realms beyond our wildest imagination. This isn't science fiction. These are the groundbreaking theories brewing in the minds of today's brightest scientists. Ideas so revolutionary they could shatter our understanding of existence itself. And right now, you're about to step into that world. Think about the last time you looked up at the night sky and felt that humbling sense of wonder. That feeling is just a glimpse of the mysteries waiting to be unraveled. Behind the quiet glow of distant stars lies a universe teeming with unanswered questions. What if dark energy is slowly rewriting the laws of physics? Could our entire reality be nothing more than a hologram, a cosmic illusion projected from the edges of space? These aren't just thought experiments. They're real theories, backed by cutting-edge research, and they're poised to ignite the next scientific revolution. This journey isn't just for astrophysicists or mathematicians. It's for anyone who's ever dared to question, to dream, to look beyond the obvious. Over the course of this video, we'll dive into 30 of the most astonishing cosmic theories ever proposed, each one a potential key to unlocking the universe's deepest secrets. From the mind-bending possibilities of quantum consciousness to the eerie connections between distant galaxies, these ideas don't just challenge science, they redefine what's possible. So buckle up. By the time we're done, you might never see the cosmos the same way again. What if the universe around us, the stars, planets, and even the screen you're staring at right now isn't actually three-dimensional? The holographic principle flips our perception of reality on its head, proposing that everything we experience might be nothing more than a projection, like a movie playing on the surface of an unimaginably vast cosmic screen. Imagine taking a holographic sticker, a flat, two-dimensional surface, and shining light through it to create a three-dimensional image. Now, scale that up to the size of the cosmos. According to this theory, the entire universe could work the same way, with all the information that makes up reality encoded on a distant, two-dimensional boundary, possibly at the edge of space itself. This isn't just wild speculation. The idea emerged from studying black holes, those enigmatic cosmic traps where gravity is so strong that not even light can escape. When matter falls into a black hole, what happens to the information it contains? Quantum physics says information can't be destroyed, yet black holes seem to erase it. The holographic principle offers a solution. The information isn't lost, it's smeared across the black hole's event horizon, the point of no return, like data etched onto a celestial hard drive. Physicists like Leonard Susskind and Gerard T. Hooft realized that if this works for black holes, maybe it applies to the entire universe. Think about the implications. If reality is a hologram, it means the three-dimensional world we see and touch is just an illusion, a kind of cosmic mirage. The true source code of existence exists somewhere else, on a flat, distant surface we can't perceive. This could be the missing link between Einstein's theory of gravity and the bizarre rules of quantum mechanics, two frameworks that have stubbornly refused to unite. The holographic principle might finally bridge that gap, revealing a deeper layer of reality where space and time aren't fundamental, just emergent properties of something far stranger. But here's the real kicker. If this theory is correct, it means the universe has a maximum amount of information it can contain, just like a computer has limited storage. There's a cosmic pixel size, a smallest possible bit of reality. That would fundamentally change how we understand everything, from the birth of the cosmos to the nature of consciousness itself. Are we living inside a simulation? Not exactly, but the holographic principle suggests reality might be even weirder than that. And if scientists can find evidence for it, we might be on the verge of rewriting the textbooks of physics forever. What if the universe we experience isn't the base layer of reality but an elaborate simulation, like a video game rendered by an unfathomably powerful computer? The simulation hypothesis suggests that everything, every star, every atom, even the thoughts in your mind, could be nothing more than lines of code in a vast digital construct. Philosopher Nick Bostrom laid the groundwork for this idea with a startling argument. If a civilization ever reaches the technological capability to create hyper-realistic simulations of its ancestors, and if that civilization has even a modest desire to run such simulations, the number of simulated minds would vastly outnumber real ones. Statistically speaking, the odds would overwhelmingly favor us being among the simulated rather than the simulators. Tech moguls like Elon Musk have amplified this debate, pointing out that if technological progress continues at its current pace, creating indistinguishable virtual worlds might be inevitable. After all, look how far video games have come in just a few decades, from simple pixels to immersive virtual realities. Extrapolate that progress over thousands or millions of years, and the line between simulation and real life could vanish entirely. Some physicists counter that simulating every particle in a universe would require impossible amounts of computational power. But what if the simulation only renders what's being observed, like a video game that loads details only when a player looks at them? Quantum mechanics already hints at something similar: particles existing in probabilistic states until measured, almost as if reality conserves processing power until needed. This theory doesn't just challenge our place in the cosmos, it redefines the meaning of existence. If we're living in a simulation, who or what wrote the code? Are the laws of physics just programmed parameters, adjustable at will by unseen engineers? Could glitches in the matrix, like déjà vu or unexplained cosmic anomalies, be bugs in the system? The implications ripple into philosophy, religion, and even ethics. If consciousness is simulated, does it still hold intrinsic value? And if our reality is artificial, what lies outside it? While there's no definitive proof, yet some scientists have proposed ways to test the simulation hypothesis. One approach looks for pixelation in the fabric of reality, tiny inconsistencies in the energy of cosmic rays that might reveal the underlying resolution of the universe, like spotting the seams in a digital image. Others suggest that if the universe is a simulation, it might rely on mathematical shortcuts, leaving detectable fingerprints in the behavior of particles at extreme energies. Until then, the theory remains a profound thought experiment, forcing us to confront the unsettling possibility that the cosmos might not be what it seems. And if it's true, the next question is even more extraordinary. What happens when the simulation ends? What if every choice you've ever made, every path taken or left unexplored, exists simultaneously in an infinite web of parallel realities? The multiverse theory takes the strangeness of quantum mechanics and stretches it across an unimaginable cosmic canvas, where countless universes bubble into existence, each with its own unique set of physical laws and alternate histories. Picture a vast ocean of soap bubbles, each one a self-contained universe, floating in an endless sea of possibilities. In one bubble, gravity might be 10 times stronger, crushing stars into oblivion before life can emerge. In another, the constants of nature align just right to birth civilizations far older and wiser than our own. And somewhere out there, another version of you might be living a life where every decision branched in a different direction. This isn't just poetic speculation, it's a serious scientific framework with roots in quantum mechanics and string theory. When particles behave unpredictably at the quantum level, existing in multiple states until observed, some physicists argue those unobserved states don't vanish. Instead, they split off into new timelines, birthing alternate universes where every possible outcome plays out. Think of it like a cosmic choose-your-own-adventure book where every page turn spawns a new reality. String theory takes it further, suggesting higher-dimensional brains could collide or drift apart, creating pocket universes with entirely different physics. The implications are staggering. If the multiverse exists, it could explain one of science's greatest mysteries: why our universe seems perfectly fine-tuned for life. The fundamental constants, like the strength of gravity or the mass of an electron, are so precisely calibrated that even slight changes would render life impossible. Coincidence unlikely, but in a multiverse, every possible configuration exists somewhere. We just happen to inhabit the rare universe where conditions allow us to ponder the question. Yet the most haunting question remains: could we ever detect these alternate realities? Some theories suggest gravitational waves or cosmic microwave background anomalies might carry echoes of collisions with other universes. Others propose that quantum entanglement, spooky action at a distance, could be a faint signal bleeding through from a parallel world. While proof remains elusive, the multiverse challenges us to rethink not just our place in the cosmos, but the very nature of existence. Are we one thread in an infinite tapestry, or is reality even stranger than we dare imagine? Now, let's push further into the unknown. What if these parallel universes aren't just distant bubbles, but layers of reality stacked atop our own, invisible yet intertwined? The idea of hidden dimensions isn't science fiction. It's a mathematical necessity in string theory, which requires at least 10 dimensions to make the equations work. We perceive only 4, 3 of space and 1 of time. But what if the others are curled up so tightly, like microscopic origami, that we'd need a particle accelerator the size of a galaxy to glimpse them? Or what if they're right beside us, warping the fabric of reality in ways we're only beginning to suspect? Consider gravity's puzzling weakness compared to other forces. It's so feeble that a tiny magnet can overpower Earth's gravitational pull on a paperclip. Why? One radical explanation: gravity isn't weak. It's just leaking into hidden dimensions, diluting its strength in our visible universe. If true, this could revolutionize physics, merging quantum mechanics and relativity into a single theory of everything. Experiments like the Large Hadron Collider hunt for evidence of these extra dimensions by searching for particles that momentarily vanish, slipping into unseen realms before snapping back into ours. The stakes couldn't be higher. Discovering hidden dimensions wouldn't just rewrite textbooks, it would unlock technologies straight from sci-fi, like energy tapped from alternate realities or shortcuts through space-time for interstellar travel. But it also raises eerie possibilities. Could these dimensions harbor exotic forms of matter or intelligence? Are dark matter and dark energy, the mysterious substances dominating our cosmos, artifacts of interactions with these unseen layers? Every unanswered question in physics might hinge on dimensions we've yet to perceive, waiting just beyond the edge of our understanding. Time might feel like an unstoppable river, flowing from past to future, but what if that's just an illusion, a trick of perception? Some of the most radical theories in physics suggest time isn't fundamental at all. Instead, it could emerge from something deeper, like the way temperature arises from the motion of particles we can't see. Imagine watching a movie. The story feels fluid, but it's really just a series of still frames flashing by. the universe might work the same way, with time as a cosmic projection, stitched together by underlying laws that don't actually contain time at all. This idea finds its boldest expression in the block universe theory, which treats reality like a four-dimensional loaf of bread. Every moment past, present, and future exists simultaneously, stacked together like slices in that loaf. To a hypothetical observer outside time, your birth, this very moment, and events 1,000 years from now would all be equally real, just at different coordinates in space-time. Albert Einstein hinted at this when he wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion." If he was right, free will takes on an eerie new light. Your choices might feel real, but in the block universe, they'd be like footprints frozen in the sand, already part of the landscape. Quantum mechanics adds another twist. At microscopic scales, particles don't seem to care about time's arrow. Reactions can run backward as easily as forward, and particles pop in and out of existence without a clear cause. Some physicists, like Carlo Rovelli, argue time emerges only when these quantum events become large enough to decohere, like ripples merging into a wave. In this view, time isn't a backdrop to the universe, it's a side effect of how we interact with it, a story our brains tell to make sense of chaos. The implications are staggering. If time is an illusion, then death might not be an endpoint, just another coordinate in the block. The future could be as fixed as the past, raising haunting questions about destiny and meaning. Even our search for cosmic origins would shift. Without time, the Big Bang wouldn't be a beginning, just a location in the grand architecture of reality. Experiments today are testing these ideas, from quantum clocks that tick differently under extreme gravity to simulations where time emerges from timeless networks. If they succeed, we might need to rewrite not just physics, but the very way we experience being alive. Now consider this: if time is fluid, could space be equally malleable? The next theory doesn't just challenge our place in the cosmos, it suggests the universe might be alive in ways we've barely begun to fathom. Could the very essence of human consciousness arise from the bizarre dance of quantum particles? This radical idea, quantum consciousness, suggests that our awareness isn't just a byproduct of electrical impulses in the brain, but something far deeper, woven into the fabric of reality itself. At the heart of this theory lies a surprising suspect: microtubules, tiny protein structures inside neurons that might act as quantum computers, processing information at scales smaller than atoms. Nobel laureate Roger Penrose and anesthesiologist Stuart Hameroff proposed that these microscopic structures could harness quantum vibrations, collapsing wave functions to generate moments of subjective experience. In other words, your thoughts, your sense of self, even the vividness of a sunset might all emerge from quantum processes humming beneath the surface of classical biology. The implications are staggering. If consciousness taps into quantum mechanics, it would mean the human mind isn't just observing the universe, it's actively participating in its quantum weirdness. This could explain why artificial intelligence, for all its computational power, still lacks genuine awareness. Current AI operates on classical physics, crunching data without true understanding. But if consciousness requires quantum coherence, delicate, orchestrated interactions between particles, then replicating it might demand an entirely new kind of technology, blending biology with quantum computing. Imagine future machines that don't just simulate thought but experience it, bridging the gap between silicon and sentience. Critics argue the brain is too warm and chaotic for fragile quantum states to survive. Yet nature has proven adept at harnessing quantum effects in unexpected places. Photosynthesis uses quantum coherence to optimize energy transfer in plants. and birds might navigate using quantum entanglement in their eyes. If biology already exploits these phenomena, why not consciousness? Experiments are underway, from studying anesthetic gases that disrupt microtubule activity to searching for quantum signatures in neural networks. The results could redefine not just neuroscience but our place in the cosmos. Philosophically, this theory blurs the line between mind and universe. If quantum processes underpin consciousness, does that mean reality requires an observer to truly exist? Some interpretations of quantum mechanics suggest particles remain in probabilistic limbo until measured. Could consciousness itself be the measuring device, collapsing possibilities into concrete experience? This isn't just about human brains. It hints that awareness might be a fundamental feature of reality, like gravity or light. The universe might not just contain consciousness, it might be built from it. Now let's turn to another cosmic enigma, dark matter. This invisible substance outweighs visible matter 5 to 1, sculpting galaxies with its gravitational pull, yet leaving no trace beyond its shadowy influence. What if the key to unlocking it lies not in distant telescopes, but in the quantum fabric of reality itself? Dark matter isn't just a missing piece of the cosmic puzzle. It's an entire hidden dimension of reality, silently shaping the universe while remaining utterly invisible to our eyes and instruments. Picture an iceberg floating in the ocean. What we see, the stars, galaxies, and glowing gas clouds, is just the tiny visible peak. Beneath the surface lies something far larger and stranger, a shadowy realm that makes up nearly 85% of all matter in existence. We know it's there because its gravitational pull bends light, spins galaxies faster than they should, and sculpts the vast cosmic web that threads through the universe. Yet, despite decades of searching, dark matter refuses to show itself directly. Why? One compelling theory suggests dark matter belongs to a parallel universe, a mirror world with its own particles and forces, barely interacting with ours except through gravity. Imagine two sheets of paper stacked together but never touching, each with its own rules, its own physics. Occasionally, a faint whisper passes between them, just enough to tug on stars and galaxies from the shadows. This shadow universe idea isn't pure speculation. Experiments like the Large Hadron Collider are hunting for hypothetical particles like WIMP, weakly interacting massive particles, that could be the hidden architects of this invisible realm. If they exist, they drift through Earth like ghosts, leaving only the faintest trace in ultra-sensitive detectors buried deep underground. But what if dark matter isn't made of particles at all? Another daring hypothesis proposes it could be a swarm of primordial black holes, forged in the chaos of the Big Bang. These wouldn't be the black holes we know, born from collapsing stars, but tiny, ancient ones, some no heavier than an asteroid yet dense enough to warp spacetime around them. They'd be nearly impossible to spot unless one passed between us and a distant star, bending its light like a cosmic magnifying glass. Recent gravitational wave detections have reignited interest in this idea, as some signals match what these primordial relics might produce if they collided. Then there's the most mind-bending possibility. Dark matter could be evidence of extra dimensions. If gravity leaks into hidden spatial dimensions, as some string theory models suggest, its apparent weakness in our universe might just be a side effect, a force diluted across realities we can't perceive. In this scenario, dark matter isn't a thing at all but a shadow cast by the true structure of the cosmos, a structure far more complex than our three-dimensional minds can grasp. The stakes couldn't be higher. Unraveling dark matter wouldn't just fill a gap in our equations, it could rewrite the story of cosmic evolution. Galaxies shouldn't have formed as quickly as they did without dark matter's gravitational scaffolding. Life itself might owe its existence to this invisible hand, which gathered the first stars and planets out of the primordial darkness. And if dark matter truly is a gateway to hidden dimensions or parallel universes, the discovery would dwarf every scientific revolution in history. We're not just hunting for a particle, we're peering into the unseen foundations of reality, where the answers might be stranger than anything we've dared to imagine. Now consider this: if dark matter is the universe's silent architect, what other invisible forces might be at work? The next theory doesn't just challenge our understanding of matter, it suggests the vacuum of space itself might hold the key to the cosmos' greatest mysteries. Einstein called them bridges, but we know them as wormholes, cosmic shortcuts that could fold the vast distances of space like a piece of paper, connecting points light-years apart in an instant. Picture the universe as a stretched bedsheet. Place two heavy marbles on opposite ends, and they'll create dimples in the fabric. Now imagine pinching those dimples together until they touch, forming a tunnel through the sheet. That's the essence of a wormhole, a hypothetical passage through spacetime's wrinkles, where entering one end could spit you out near a distant star, or even in another universe entirely. The math checks out. Einstein and physicist Nathan Rosen first theorized these structures in 1935, showing how general relativity permits tunnels between black holes. But there's a catch: wormholes would snap shut faster than you could say, interstellar road trip, unless held open by something with negative energy, exotic matter that defies gravity's pull. Think of it like cosmic duct tape propping open the throat of the wormhole against the relentless crush of spacetime. No known substance fits the bill, but quantum physics offers a glimmer of hope. Virtual particles which pop in and out of existence in empty space sometimes exhibit negative energy. Could we harness them? Theoretical models suggest microscopic wormholes might already exist at the Planck scale, smaller than an atom, woven into the quantum foam of reality itself. The implications are staggering. If traversable wormholes exist, they wouldn't just revolutionize space travel, they'd rewrite the rules of causality. Step through one end, and you might emerge before you left, creating paradoxes that make time travel look simple. Some theories even propose wormholes could be entangled quantum particles stretched across spacetime, linking distant points like cosmic walkie-talkies. This might explain spooky quantum entanglement, where particles instantly influence each other across vast distances, as if whispering through a hidden tunnel. Yet the biggest question remains: could we ever find one? Wormholes wouldn't announce themselves with flashing signs. They might lurk in the gravitational shadows of black holes or masquerade as cosmic mirages, bending light in ways we're only beginning to model. Recent simulations suggest certain wormholes could mimic black holes so precisely that even our telescopes might be fooled. The key difference: black holes trap everything, while wormholes might let some light or something else escape through the other side. Future gravitational wave detectors or quantum experiments might finally spot their fingerprints, revealing whether these space-time shortcuts are more than just equations on a chalkboard. But here's the twist: if wormholes exist, they might not be natural at all. Advanced civilizations far older than ours could have engineered them as cosmic highways, stitching the universe together like a grand subway system. The Fermi paradox asks why we haven't met aliens yet. Maybe the answer isn't that they're absent, just that they're traveling routes we can't yet see. Whether natural or artificial, wormholes tease us with the possibility that the universe is far more connected and far stranger than we've dared to dream. And if we ever unlock their secrets, the stars might finally be within reach. White holes are the cosmic rebels of theoretical physics, black holes elusive twins playing by opposite rules. While black holes devour everything that crosses their event horizons, white holes spit matter and energy outward with unstoppable force, slamming their doors shut to any would-be intruders. Picture a black hole in reverse. Instead of a cosmic vacuum cleaner, it's a fire hose blasting particles into space at unimaginable speeds. The equations of general relativity allow for such objects, but no one has ever spotted one. So why do scientists take them seriously? Because white holes might solve two of the universe's greatest riddles: the fate of dying black holes and the origin of existence itself. Let's start with black hole evolution. When a black hole evaporates over eons via Hawking radiation, losing mass until it potentially vanishes, what happens to the singularity at its core? One radical idea suggests it doesn't disappear but rebounds as a white hole, transforming the black hole's crushing gravity into an explosive burst of energy. This quantum bounce could recycle matter and spacetime in a cosmic reset, like a phoenix rising from the ashes. If true, white holes might be scattered throughout the universe, remnants of ancient black holes that underwent this spectacular metamorphosis. Some researchers even propose that mysterious high-energy events, like certain gamma-ray bursts with no obvious source, could be white holes announcing their presence across cosmic distances. But the wildest hypothesis ties white holes to the very beginning of everything. What if the Big Bang wasn't a singularity but a white hole's grand finale? In this scenario, our universe isn't the result of an unfathomably dense point exploding outward. It's the aftermath of a white hole from a parent universe, funneling matter and energy into our spacetime like a cosmic exhaust port. This wouldn't just redefine the Big Bang, it would embed our universe within an infinite fractal of others, each born from the death throes of a white hole in a higher dimensional reality. The catch: white holes violate the second law of thermodynamics by seemingly creating order from chaos, spewing out pristine energy without an obvious source. That's why many physicists argue they're mathematical curiosities, not physical realities. Yet nature has surprised us before. After all, black holes were once considered theoretical fantasies until evidence proved otherwise. Could white holes be hiding in plain sight, masquerading as unexplained cosmic explosions or even dark energy's mysterious fingerprints? Speaking of dark energy, this enigmatic force is stretching the universe apart at an accelerating rate, a discovery that earned a Nobel Prize but left scientists baffled. What if dark energy isn't a force at all, but the collective sigh of countless white holes exhaling matter into the void? Or perhaps spacetime's hidden dimensions are leaking energy into our universe, driving its expansion like an invisible engine? The answers might lie in the quantum shadows where black holes end and white holes begin, rewriting not just the fate of collapsed stars, but the destiny of the cosmos itself. Dark energy isn't just a mystery, it's the universe's greatest unsolved riddle, an invisible force pushing galaxies apart faster and faster, as if space itself has a mind of its own. Imagine blowing up a balloon with tiny dots on its surface. As the balloon expands, the dots move away from each other. Now, picture someone cranking up the air pump, making the balloon inflate at an ever-increasing speed. That's dark energy in action, stretching the cosmic fabric so violently that distant galaxies will one day vanish over the horizon of observation, leaving future civilizations with a sky nearly empty of stars. But what is this enigmatic force? One leading theory suggests dark energy is woven into the very fabric of space, a property Einstein once called the cosmological constant. Empty space, far from being nothing, might possess an intrinsic energy that generates repulsive gravity, counteracting the pull of matter and driving the universe's acceleration. It's like trying to swim against a current that gets stronger the harder you fight. But there's a problem. When physicists calculate how much energy empty space should contain based on quantum theory, the numbers overshoot observations by a staggering factor of 1 followed by 120 zeros. This vacuum catastrophe hints that either our math is wildly off or dark energy is something far stranger. Enter quintessence, a dynamic field that permeates the cosmos, fluctuating over time like an invisible ocean with shifting tides. Unlike the static cosmological constant, quintessence could change in strength, potentially growing more dominant or fading away as the universe ages. If it strengthens, the consequences are apocalyptic. Galaxies would first be ripped from their clusters, then stars from their galaxies, and finally, atoms would be torn apart in a cataclysm cosmologists call the Big Rip. Time itself could lose meaning as the fundamental bonds holding reality together snap. Yet there's another, even more unsettling possibility. Dark energy might not be a force at all, but an illusion created by our incomplete understanding of gravity. Just as Newton's laws were superseded by Einstein's relativity, our current physics might be missing a deeper layer of cosmic mechanics. Some theorists propose that gravity behaves differently on universe-sized scales, mimicking the effects of dark energy without any exotic substance required. Others suggest we're seeing echoes of hidden dimensions or the gravitational leakage from parallel universes pressing against our own. The stakes couldn't be higher. Dark energy doesn't just shape the universe's fate, it holds the answer to whether reality will end in ice or fire, in infinite expansion or a dramatic collapse. And if we ever unravel its secrets, we might discover that the force dooming the cosmos is also the key to unlocking its deepest truths. But before we resign ourselves to a dark energy-dominated future, let's turn to a theory that flips the script entirely, one where the universe isn't expanding toward oblivion, but cycling through rebirths in an endless cosmic dance. Quantum immortality twists the multiverse theory into a cosmic hall of mirrors, where death might be an illusion and consciousness could be the ultimate survivor. Imagine you're playing a high-stakes game of Russian roulette with a revolver. In most universes, the trigger pulls and the story ends, but according to this mind-bending idea, your subjective experience would only continue in the timelines where the chamber is empty, because in the others, there's no you left to perceive the outcome. Over infinite trials, there's always at least one universe where you improbably survive, creating the eerie sensation that you're somehow cheating fate. This isn't just speculative fiction, it's a thought experiment rooted in the many worlds interpretation of quantum mechanics. Every quantum event, like the decay of a radioactive atom, spawns branching realities. If consciousness is tied to these quantum outcomes, your awareness might naturally follow the paths where you persist, no matter how unlikely. The mathematician Max Tegmark famously illustrated this by imagining a suicide machine that activates based on a quantum measurement. Statistically, most versions of you would die, but from your perspective, you'd always witness the 1 in a billion outcome where the machine fails. The implications are as unsettling as they are profound. If quantum immortality holds, it would mean death is never truly experienced, only avoided, at least from your first-person viewpoint. Aging, accidents, even the heat death of the universe might not be in points, just milestones in an unbroken chain of conscious moments strung together across realities. Some theorists take this further, suggesting that near-death experiences, those vivid flashes of tunnels and light, could be glimpses of consciousness shifting to a timeline where survival was possible. But here's the catch: quantum immortality isn't a license to recklessness. Even if countless versions of you perish, you wouldn't remember those branches. And the surviving versions might not be pleasant. A car crash could leave you permanently injured in one universe while obliterating you in others. The theory also grapples with deep philosophical questions. What defines you across these branches? If your memories and body diverge, is it still immortality, or just a series of close calls strung together by chance? Critics dismiss the idea as untestable metaphysics, a clever but ultimately empty thought experiment. Yet it forces us to confront the nature of observation and existence. If consciousness truly shapes reality at the quantum level, then the line between physics and philosophy blurs beyond recognition. And if nothing else, quantum immortality serves as a haunting reminder. The universe might be far stranger than our classical senses suggest. Now let's pivot from the mysteries of consciousness to a theory that redefines one of the universe's most fundamental forces. What if gravity isn't a force at all, but a shadow cast by something deeper, a cosmic illusion hiding the true fabric of reality? What if gravity, the force that pins us to Earth and guides the dance of galaxies, isn't a fundamental force at all, but a side effect of something far stranger happening beneath the surface of reality? Physicist Eric Verland's radical theory of emergent gravity proposes exactly that, suggesting gravity isn't an intrinsic feature of the universe, but an illusion emerging from the chaotic interplay of quantum information. Picture a crowd at a concert. From a distance, the movement of people looks smooth and predictable like a wave, but up close, it's just individuals jostling in unpredictable ways. Gravity, in this view, might be the large-scale pattern we mistake for a fundamental force, while the real action happens at the quantum level, where bits of information interact in ways we're only beginning to grasp. At the heart of Verland's idea lies entropy, a measure of disorder that, counterintuitively, might be the key to order in the cosmos. Just as heat emerges from the random motion of molecules, gravity could arise from the way information is distributed and rearranged on the fabric of spacetime. Think of spacetime as a vast cosmic hard drive, with every particle and energy fluctuation encoding data. When matter distorts this drive, it creates gradients in entropy, and those gradients manifest as what we perceive as gravity. This isn't just poetic metaphor. The math suggests that Newton's famous law of gravitation and even Einstein's general relativity could be approximations of this deeper information-theoretic process. The implications are staggering. If gravity emerges from entropy, it could solve one of astronomy's biggest headaches, dark matter. Galaxies rotate so fast that, according to conventional gravity, they should fling themselves apart. Dark matter was proposed as an invisible glue holding them together, but what if we don't need it? Verland's equations predict the same galactic behavior without invoking mysterious particles, suggesting dark matter's gravitational effects might just be entropy in disguise. It's as if we've been searching for ghosts to explain shadows on the wall, only to realize the wall itself is casting them. Critics argue emergent gravity hasn't yet passed all observational tests, and it struggles to explain phenomena like the bullet cluster, where colliding galaxies seem to separate dark matter from visible matter. But supporters counter that our understanding of quantum information is still in its infancy. After all, Einstein's relativity once seemed outlandish too, until eclipses and orbiting pulsars proved him right. If emergent gravity holds up, it wouldn't just rewrite physics textbooks, it would redefine our place in the cosmos. We're not passive observers of a universe governed by fixed laws. We're participants in a dynamic, computational dance where gravity is less a force and more a cosmic byproduct of reality's hidden code. Now here's where it gets even wilder. If gravity emerges from information, what does that say about the nature of spacetime itself? The holographic principle suggests our three-dimensional universe might be a projection of data stored on a two-dimensional surface at its boundary. Emergent gravity dovetails eerily with this idea, hinting that the universe isn't just described by information, it might literally be information. the solidity of planets, the pull of black holes, even the arrow of time could all be shadows cast by quantum bits we can't yet see. This isn't just science flirting with philosophy. It's a fundamental shift in how we understand existence. And if future experiments like precise measurements of galactic rotations or lab tests of quantum entropy confirm these ideas, we might be on the verge of a revolution that makes the quantum leap from Newton to Einstein look like a small step. Black holes have always been seen as cosmic destroyers, gaping maws where matter vanishes forever. But what if they're actually creators? The theory of black hole cosmology flips the script entirely, proposing that every black hole could be the seed of an entirely new universe, nesting realities like cosmic Russian dolls. Imagine a drop of water falling into a pond. From our perspective, it disappears beneath the surface, but to a microscopic world inside that droplet, the impact might feel like a big bang, an explosion of energy birthing a new realm. According to this idea, our own universe might have begun this way, forged in the crushing depths of a black hole from a parent cosmos we'll never see. The math behind this is as elegant as it is mind-bending. Loop quantum gravity, a leading contender to unite relativity and quantum mechanics, suggests that at the heart of a black hole's singularity, space-time doesn't simply collapse into infinity. Instead, it rebounds like a spring compressed to its limit, creating an outward surge of energy that could inflate into an infant universe with its own physical laws. This means the inside of a black hole might not be a dead end but a doorway, with our entire cosmic history unfolding on the other side of an event horizon we can never cross back through. Think about the implications. If black holes are cosmic wombs, then the expansion of our universe, the galaxies racing away from each other, might just be the aftershock of that primordial rebound. Even more astonishing, this could solve one of physics' greatest puzzles: why our universe seems fine-tuned for life. The constants of nature, the strength of gravity, the mass of electrons are perfectly calibrated to allow stars, planets, and ultimately consciousness to exist. If new universes spawn inside black holes with slightly tweaked physics, only those with the right parameters would give rise to observers like us. The rest would fizzle out, empty and unobserved. We're not here because of luck. We're here because only a universe like ours could produce beings capable of asking the question. But here's where it gets truly surreal. If black holes birth universes, could our own cosmos contain civilizations thriving inside its black holes, completely unaware of us? Picture a super-advanced society orbiting a star that, from our perspective, vanished into a singularity eons ago. To them, their world might seem infinite, their night sky filled with galaxies born from their own black holes, an endless fractal of realities within realities. Communication would be impossible. The event horizon is a one-way curtain, but the idea forces us to reconsider what existence even means. Are we the main event or just one layer in an infinite cosmic onion? This theory isn't just speculative poetry. It makes testable predictions. If our universe was born from a black hole, the spin of that parent singularity might have imprinted itself on the large-scale structure of our cosmos, leaving faint patterns in the cosmic microwave background, echoes of our cosmic ancestry. Future telescopes hunting for these anomalies could find clues etched in the oldest light in the universe, and if they do, it would mean black holes aren't tombs. Their cradles, every collapsing star, every galactic core, might be cradling newborn universes in its depths, each with its own story, its own laws, its own mysteries waiting to unfold. Now let's descend even deeper into the quantum realm, where the fabric of reality flickers in and out of existence, and where the next theory suggests that space-time itself might be nothing more than a shimmering mirage. Quantum Darwinism takes the bizarre rules of the quantum realm and injects them with the ruthless logic of survival of the fittest. In the microscopic world, particles exist in a haze of probabilities. An electron isn't here or there until measured, but somehow both at once. Yet when we look around, trees, buildings, and stars appear solid and predictable. Why doesn't the quantum weirdness bleed into our everyday experience? This theory proposes an answer. The universe itself performs a kind of natural selection, where only the most stable, replicable quantum states get to stick around long enough to be observed. Think of it like a cosmic game of telephone. When a quantum system interacts with its environment, whether it's a photon bouncing off a table or an atom jostling in the air, countless tiny measurements occur. Most quantum states are fragile, collapsing under the slightest disturbance, but a few are robust enough to survive these interactions and propagate their information outward. Over time, these fittest states dominate, while the others fade into oblivion. It's as if reality itself evolves, with the classical world we see emerging from a quantum soup through a process akin to biological selection. The chair you're sitting on feels solid not because quantum uncertainty vanished, but because its stable configuration outcompeted the alternatives. This idea, championed by physicists like Wojciech, elegantly bridges the gap between the quantum and classical worlds. It suggests that the laws of physics we take for granted, gravity, electromagnetism, even the speed of light, might not be fundamental truths, but the end result of an unseen evolutionary arms race. Just as animals adapt to their niches, certain quantum states could have adapted to endure in our universe's environment, while others perished. Even the arrow of time might owe its existence to this process, with entropy favoring states that propagate forward rather than backward. But here's where it gets truly radical. If quantum Darwinism is correct, it implies that reality isn't just discovered by observation, it's shaped by it. The universe isn't a static stage, it's a dynamic ecosystem where only the most observable phenomena persist. This could explain why we perceive 3 spatial dimensions instead of 10, or why certain physical constants seem fine-tuned for complexity. They're not arbitrary, they're the survivors of a cosmic selection process older than stars. Now consider this: if reality evolves, could consciousness itself be a product of quantum selection? The next theory doesn't just blur the line between life and the cosmos, it suggests they might be 2 sides of the same coin. Panspermia turns the cosmos into a grand biological highway, where life hitchhikes between stars on comets and asteroids like microscopic stowaways. Imagine a single bacterium frozen in the icy heart of a comet for millions of years, surviving the harsh vacuum of space only to awaken on a young, watery planet like Earth. This isn't just fantasy. Scientists have found microbes thriving in Earth's most extreme environments, from boiling hydrothermal vents to the radiation-drenched heights of the stratosphere. If life can endure those conditions, why not the journey between worlds? Experiments like the European Space Agency's EXPOSE mission have shown that certain organisms, like tardigrades, can survive years in outer space by entering a state of suspended animation. Even more compelling, amino acids. The building blocks of life have been discovered on asteroids, suggesting the raw ingredients for biology might be universal cargo aboard these cosmic delivery trucks. But panspermia gets even wilder. Some versions propose directed panspermia, the idea that an ancient alien civilization intentionally seeded life across the galaxy. Picture a starship packed with microbial payloads, targeting habitable planets like a cosmic gardener scattering seeds. Nobel Prize-winning chemist Francis Crick, who co-discovered DNA's structure, entertained this possibility, noting that the sudden appearance of life on Earth seems almost too perfectly timed. If true, it would mean every living thing on our planet, from towering redwoods to hummingbirds, might share a genetic lineage with organisms engineered by beings from another world. The implications are staggering. Life could be less a lucky accident and more a deliberate cosmic project, with Earth as just one greenhouse in a vast interstellar nursery. Critics argue that interstellar radiation and the timescales involved make accidental panspermia unlikely, yet recent discoveries keep the debate alive. The interstellar object Oumuamua, which zipped through our solar system in 2017, showed that material can traverse between star systems. And if life arose independently on Mars, which once had flowing rivers and lakes, microbes could have hitched a ride to Earth on debris blasted into space by asteroid impacts. NASA Perseverance rover is now hunting for fossilized Martian microbes, and if it finds them, the similarities to Earth life could hint at a shared origin written in the stars. Whether by chance or design, panspermia reshapes our place in the universe. If life spreads like cosmic pollen, then the Milky Way could be teeming with relatives we've yet to meet, organisms built from the same genetic toolkit, adapted to worlds we can barely imagine. The next time you gaze at a meteor shower, consider this. Those fleeting streaks of light might be more than just space rocks burning up. They could be reminders that we're part of something vast, ancient, and profoundly interconnected. Now let's shift from the spread of life to the limits of speed. What if the universe's ultimate speed limit, the speed of light, isn't as fixed as Einstein believed? The next theory doesn't just bend the rules of physics. It suggests they might be written in erasable ink. Einstein's theory of relativity hinges on one unshakable constant, the speed of light. But what if that speed isn't as constant as we thought? Imagine a universe where light raced faster in its infancy, a cosmic sprint that could solve one of cosmology's biggest mysteries, inflation. In the first sliver of a second after the Big Bang, the universe expanded exponentially, stretching from smaller than an atom to the size of a grapefruit faster than light itself could cross it. Standard physics can't explain this, but if light moved quicker back then, suddenly the math aligns. Some theories, like Joe Megiddo's varying speed of light hypothesis, suggest that in the extreme heat and density of the early cosmos, light's speed might have been uncoupled from its current limit, acting as a cosmic pressure valve that smoothed out the universe's wrinkles before settling into the constant we measure today. This isn't just about the distant past. Near black holes where space-time warps into knots, light might behave in ways that defy Einstein's rules. Picture a beam of light skirting the edge of a singularity. Under such extreme gravity, could its speed flicker or slow like a car struggling up a steep hill? Modified gravity models hint that light speed could vary in these extreme environments, subtly altering how we perceive distances and time near these cosmic monsters. If true, it would mean the universe's ultimate speed limit isn't a fixed signpost but a dynamic marker, shifting with the fabric of spacetime itself. The implications would ripple through every corner of physics. GPS satellites, which rely on precise timing corrections from relativity, might need recalibration. The age of the universe, calculated using light speed as a yardstick, could be off by billions of years. Even the nature of causality, the unbreakable rule that cause must precede effect, might need rethinking if light speed isn't the universe's strict referee. Critics argue that varying light speed would leave detectable traces in the cosmic microwave background or quantum experiments, and so far, no smoking gun has been found. Yet the possibility lingers, a tantalizing what-if that challenges the foundations of modern physics. Now consider this: if light speed isn't constant, what other cosmic rules might be flexible? The next theory doesn't just tweak the universe's parameters, it suggests the cosmos might be built on a hidden symmetry, so profound it could unite all forces of nature into a single, elegant equation. Supersymmetry whispers a tantalizing secret that for every particle we know, from the humble electron to the elusive neutrino, there exists a hidden twin, a superpartner with properties just different enough to have evaded detection so far. Picture the universe as a grand cosmic mansion where we've only explored the ground floor, unaware that an entire mirrored wing exists just out of sight. These superpartners would differ in one key way: their spin, a quantum property that dictates how they interact with the fabric of spacetime. Electrons might have sleeker counterparts called selectrons, while photons could pair with photinos, particles that carry light's energy but move like shadows through ordinary matter. This isn't just mathematical whimsy. Supersymmetry, or SUSY for short, could solve some of physics' greatest puzzles in one elegant stroke. Take dark matter, the invisible glue holding galaxies together. The lightest superpartner, often dubbed the neutralino, might be the perfect candidate: stable, massive, and barely interacting with ordinary matter except through gravity. It's as if the universe handed us a cosmic Where's Waldo, hiding the answer in plain sight within equations we've had for decades. Even more compelling, SUSY could bridge the chasm between quantum mechanics and gravity, offering a path to the long-sought theory of everything. By balancing the frenetic quantum world with the smooth curvature of spacetime, supersymmetry might finally explain why the cosmos operates on two seemingly incompatible rulebooks. Yet the plot thickens. If superpartners exist, why haven't we spotted them? The Large Hadron Collider has hunted for these elusive particles for years, smashing protons together at near-light speeds to recreate conditions last seen a fraction of a second after the Big Bang. So far, nothing, but physicists aren't ready to shelve the idea. Many suspect superpartners might simply be heavier than expected, lurking just beyond our current energy reach. Others propose they're hiding in plain sight, camouflaged by decaying into particles we mistake for background noise. Future colliders, like the proposed Future Circular Collider with its 50-mile-long tunnel, could finally pry open this hidden layer of reality. Imagine the implications if they succeed. The periodic table would double overnight, revealing a zoo of new particles that rewrite chemistry, astrophysics, even the story of cosmic evolution. The universe wouldn't just be more complex, it would be fundamentally different, with every interaction we take for granted governed by unseen dances between matter and its shadowy twins. SUSY elegance lies in its audacity. It doesn't tweak reality, it doubles it, offering a mirror so perfect that reflecting our known physics might finally reveal the universe's true face. Now, let's pivot from hidden particles to an even deeper mystery, one that challenges our very perception of time's relentless march forward. What if the arrow of time isn't a universal law, but a fleeting illusion born from the chaos of the early cosmos? Retrocausality turns our everyday understanding of time inside out, suggesting the future might reach back to mold the past like clay. Picture tossing a stone into a pond, watching ripples spread outward, then seeing those ripples suddenly reverse, racing back to your hand before you even threw it. This isn't just poetic imagery. Quantum physics hints at something eerily similar happening at the smallest scales. In lab experiments, particles like photons seem to choose their properties retroactively, changing their behavior based on measurements made after they've already been detected. It's as if the universe is a cosmic game of Mad Libs where the ending fills in the blanks of the beginning. The double-slit experiment, a cornerstone of quantum weirdness, reveals this paradox in action. When particles like electrons are fired one by one toward a barrier with two slits, they create an interference pattern on the other side, as if each particle passes through both slits simultaneously, interfering with itself. But here's the twist. If scientists place detectors to observe which slit each electron actually goes through, the interference pattern vanishes. The particles behave like well-mannered classical objects. Stranger still, if you delay the decision to measure until after the electrons have already passed through the slits, a setup called the quantum eraser experiment, the interference pattern can reappear, as if the future choice retroactively rewrites the past behavior. Some interpretations, like the transactional model of quantum mechanics, take this further. They propose that waves of probability don't just flow forward in time but also backward, with future events handshaking with the past to settle on a single, consistent reality. Think of it like negotiating with a time-traveling real estate agent. The present isn't fixed until the future agrees on the terms. This could explain why quantum systems seem to know about measurements before they happen. Their states are being shaped by a dialogue across time. The implications are staggering. If retrocausality is real, free will might not be an illusion, but a negotiation between our choices and their future consequences. Time loops where information circulates endlessly between past and future could allow for self-consistent paradoxes, like a scientist receiving blueprints for a time machine from their future self, then building the same machine to send those plans back. No grandfather paradoxes, just a cosmic Ouroboros where cause and effect bite their own tails. Critics argue these ideas stretch credulity, pointing out that retrocausality risks violating the second law of thermodynamics, which gives time its arrow. Yet supporters counter that entropy might still increase overall, even if tiny quantum events dance backward. After all, the universe loves symmetry. Why should time be the exception? Future experiments like ultra-precise tests of quantum entanglement or gravitational wave detectors tuned to temporal anomalies might finally settle the debate. Until then, retrocausality remains a thrilling reminder. The universe might not just be stranger than we imagine, but stranger than we can imagine. Now, let's shift from the fabric of time to the nature of perception itself. What if consciousness isn't just a passenger in the cosmos, but an active participant in shaping reality? The next theory doesn't just bridge mind and matter, it suggests they might be inseparable from the start. Cosmic consciousness isn't just a poetic metaphor. It's a radical reimagining of reality where the universe isn't just a cold, mechanical expanse but a living, thinking entity. Picture the cosmos as a vast neural network, with galaxies acting like celestial neurons firing across the void, exchanging signals not through electrical impulses but gravitational waves and quantum entanglement. Philosopher Alfred North Whitehead once suggested that even the simplest particles might possess a flicker of experience, a proto-consciousness that scales up to the self-awareness we recognize in humans. Modern panpsychists take this further, arguing consciousness isn't something that emerges from complexity like a brain piecing together thoughts, but is instead woven into the very fabric of existence, as fundamental as space or time. Think of it like this. If you zoom in on a computer screen, you'll see pixels, tiny dots of color that seem meaningless up close. But step back, and those pixels form images, videos, entire worlds. Similarly, what if the building blocks of reality, quarks, electrons, even the fabric of space-time, carry a rudimentary form of awareness? When arranged in certain ways, like the trillions of neurons in a human brain, that awareness amplifies into what we call thought. But in a star, a black hole, a galaxy cluster, the scale of consciousness could be beyond anything we can fathom, operating on timelines so vast that a single thought might span millennia. This idea isn't just philosophical speculation. Some physicists point to the eerie fine-tuning of the universe, the precise constants that allow for stars, planets, and life, as potential evidence of a cosmic mind tweaking its own parameters. Others note that quantum systems seem to choose outcomes when observed, as if reality responds to awareness. Even the structure of the cosmos mirrors neural networks. Galaxy filaments stretch across the void like axons, with superclusters resembling synaptic junctions. The similarities are so striking that researchers have run simulations comparing the universe's large-scale structure to brain tissue, and the overlap is uncanny. But here's the haunting question. If the universe is conscious, what is it thinking about? Is our existence, our art, science, wars, and love just a fleeting ripple in its boundless awareness? Or are we, in some way, the universe's way of understanding itself? The poet Rumi once wrote, "You are not a drop in the ocean, you are the entire ocean in a drop." Panpsychism flips that into a scientific framework, suggesting every atom in your body hums with the same primordial awareness that spins galaxies and ignites stars. Now let's take this one step further. If consciousness is universal, could the Big Bang itself have been more than an explosion, perhaps a cosmic awakening? The next theory doesn't just explore the universe's birth. It suggests the entire cosmos might be a living, evolving entity with its own life cycle. Conformal cyclic cosmology spins the tale of the universe into an endless epic, where each Big Bang isn't a beginning but a rebirth, a cosmic phoenix rising from the ashes of a previous era. Roger Penrose's audacious theory paints time not as a straight line but as an infinite loop, where the distant future of one universe becomes the fiery dawn of the next. Imagine closing the final chapter of a book, only to find the last sentence bleeding into the first page of a new volume, again and again, forever. At the heart of this cycle lie black holes, those enigmatic cosmic destroyers that might secretly be the architects of new realities. As a universe expands toward heat death, its black holes slowly evaporate via Hawking radiation, leaving behind only massless particles like photons. In this sparse, featureless void, Penrose proposes, the universe becomes indistinguishable from the ultra-smooth, low-energy state of a new Big Bang, bridging the end of one cycle to the start of another in a seamless cosmic handoff. The smoking gun for this mind-bending idea might be etched in the oldest light we can see, the cosmic microwave background. Penrose and his collaborators claim to have spotted Hawking points, circular patches of slightly warmer radiation that could be the imprints of supermassive black holes from a previous universe, their evaporating energy leaving faint scars on the sky. These anomalies, if confirmed, would be like finding fingerprints on a freshly painted wall, hints that our universe isn't the first iteration but merely the latest in an endless series. Critics argue these patterns could be statistical flukes, but if they're real, they'd rewrite not just cosmology but the very meaning of existence. Time would lose its arrow, becoming a Möbius strip where beginnings and endings are illusions, and every universe inherits the quantum whispers of its ancestors. What's staggering is the implication for entropy, the measure of disorder that supposedly dooms our universe to a cold, lifeless end. In Penrose's model, the exponential expansion of space doesn't just stretch matter thin. It effectively resets entropy's clock, ironing out wrinkles so completely that the next cycle starts fresh. It's as if the universe has a built-in recycling system, where the thermodynamic trash of one epoch becomes the pristine raw materials of the next. This could explain why our universe seems so finely tuned for complexity. If infinite cycles have already played out, the parameters that allow for stars, planets, and life might be the ones that persist, honed by cosmic trial and error across eons we can't fathom. Now shift your gaze from the vast scales of collapsing universes to the quantum void beneath our feet. If space isn't empty but a seething foam of virtual particles popping in and out of existence, could this vacuum hold the key to an even deeper mystery, the origin of everything from nothing? The boundary between physics and philosophy blurs when we confront the void, where the rules of causality twist and the universe might owe its existence to a quantum fluctuation so vast it birthed reality itself. The quantum vacuum isn't the barren void we once imagined. It's a seething ocean of energy, crackling with particles that flicker in and out of existence so fast they defy detection. This zero-point energy, the lowest possible energy state of a quantum system, isn't just theoretical. It's the reason atoms never truly sit still, their electrons jittering even at absolute zero, as if the universe itself refuses to let them rest. Picture the vacuum like a pot of water boiling at the smallest scales, with virtual particles, electron and anti-electron pairs, quarks and antiquarks constantly bubbling up from nowhere, only to annihilate each other in a flash. These aren't just mathematical quirks, they produce measurable effects like the Casimir force, where two metal plates placed nanometers apart in a vacuum are inexplicably pushed together by the sheer pressure of these quantum fluctuations. Now here's where it gets revolutionary. If the vacuum isn't empty but brimming with infinite energy, could we harness it? Imagine a civilization no longer reliant on fossil fuels or even starlight, but drawing power from the fabric of space itself. The idea isn't pure fantasy. Some theoretical models suggest that if we could stabilize virtual particles capturing them before they vanish, we might unlock a source of clean, boundless energy. The challenges are staggering. Quantum fluctuations operate on scales trillions of times smaller than atoms, and the energy required to extract usable power might outweigh the yield. Yet the tantalizing possibility remains, like tapping into the cosmic equivalent of a battery woven into the universe's very structure. But zero-point energy might hold an even deeper secret. It could be the elusive dark energy accelerating the universe's expansion. If the quantum vacuum's energy density isn't perfectly balanced, its repulsive gravity might be stretching space-time apart, pushing galaxies away from each other faster and faster. This would mean the fate of the cosmos hinges on the behavior of particles we can't even directly observe. Critics argue that calculations of zero-point energies magnitude overshoot dark energy's observed effects by a factor of 10 to the power of 120, a discrepancy so vast it's been called the worst theoretical prediction in physics. But perhaps we're missing a piece of the puzzle, a hidden symmetry or undiscovered law that reconciles the math with reality. The implications ripple beyond energy and cosmology. If zero-point fluctuations are real and omnipresent, they might influence everything from the stability of matter to the very arrow of time. Some researchers even speculate that consciousness itself could interact with this quantum foam, our observations somehow crystallizing fleeting probabilities into the solid world we perceive. Whether we're standing on the brink of an energy revolution or staring into the abyss of a cosmic mystery, one thing is clear: the void isn't empty. It's alive with potential, whispering secrets about the universe's deepest workings, if only we can learn to listen. Now let's stretch our imagination beyond 3 dimensions, where the next theory suggests that reality might be far grander and far stranger than our senses can perceive. Brane cosmology turns the universe into something straight out of a sci-fi novel, a 3-dimensional island adrift in a hidden sea of higher dimensions. Picture a soap bubble floating in a room you can't see, its shimmering surface a universe unto itself, while just beyond its membrane lies an expanse of reality our senses can't grasp. This is the bold vision of string theory, where what we call the cosmos isn't the whole story but merely a slice, a brane, short for membrane, suspended in a vast, multidimensional bulk. And here's where it gets wild. If other branes exist nearby, parallel universes could be hovering mere millimeters away in dimensions folded too tightly for us to perceive. The real kicker, these branes aren't static. They move, vibrate, and crucially collide. One leading theory suggests the Big Bang wasn't a singular explosion from nothingness, but the aftermath of two branes smashing together in the higher dimensional bulk. Imagine two sheets of paper drifting in a breeze until they slap together with enough force to ignite an entire universe in their wake. The energy of that collision would flood our brain with heat, matter, and the seeds of galaxies, all while the higher dimensional drama remains invisible to us. This ekpyrotic universe model, championed by physicists like Paul Steinhardt, offers an elegant alternative to cosmic inflation, explaining the universe's uniformity without invoking a mysterious burst of faster-than-light expansion. But the implications go far beyond origins. If branes are real, gravity's puzzling weakness compared to other forces might finally make sense. While electromagnetism and nuclear forces are trapped on our brain like ink on paper, gravity could be leaching into the bulk, its strength diluted across dimensions we can't access. That's why a magnet can overpower Earth's gravity on a paperclip. The other forces are concentrated here, while gravity spills into the cosmic shadows. Future experiments hunting for deviations in gravity at microscopic scales might catch whispers of these extra dimensions, like sensing a hidden room by the draft under a door. Now let's talk neighbors. If other branes drift through the bulk, some could harbor universes with radically different physics realms where gravity is 1,000 times stronger, or where time flows backward. Worse yet, a nearby brane might not be empty. It could host another three-dimensional world, separated from ours by less than the width of a human hair in a higher dimension. Collisions between branes might not just be ancient history. They could recur in cycles, with each crash resetting the cosmic clock in an endless cycle of creation and destruction. The most haunting possibility: dark matter might not be matter at all, but the gravitational tug of a parallel brane hovering just out of reach, its mass warping our universe from the shadows. It's as if we've been straining to see a ghost, only to realize we're the ones trapped in the mirror. Whether branes are the key to unification or just a beautiful mathematical mirage, one thing is certain: reality, as we know it, might be thinner than we ever dared to dream. Prion Theory dares to ask a question that unsettles the very foundations of particle physics. What if the building blocks we call fundamental aren't so fundamental after all? For decades, scientists have treated quarks and leptons, the particles that make up protons, neutrons, and electrons, as indivisible dots at the bottom of reality's ladder. But what if these dots have their own hidden architecture? Imagine zooming in on a grain of sand only to find it's a mosaic of even tinier crystals, each with its own structure and rules. That's the radical promise of Prion's hypothetical subquark particles that could rewrite our understanding of matter's deepest layers. The motivation behind Prion theory is elegance. The standard model of particle physics catalogs a zoo of seemingly unrelated particles: 6 types of quarks, 6 leptons, and their antimatter twins. Why so many, and why do they have the specific masses they do? Prions offer a tantalizing solution. If quarks and leptons are composites of just a handful of prions, like different Lego structures built from the same basic bricks, their diversity could emerge from simple combinations. A neutron's heft, an electron's lightness, even the ghostly neutrality of a neutrino might all trace back to how prions bind together in the quantum equivalent of origami. Some models propose as few as 2 prion types, with their interactions mediated by a new force far stronger than the nuclear glue holding atoms together. Yet the hunt for prions faces a cosmic-sized obstacle: energy. To smash quarks apart, if they even can be split, we'd need colliders with energies millions of times greater than today's Large Hadron Collider, machines the size of solar systems. Some theorists suggest we might spot indirect clues instead, like subtle anomalies in high-energy particle decays or patterns in cosmic rays that defy standard model predictions. Others argue prions could explain why no isolated quark has ever been observed. They're eternally bound because prion forces grow stronger with distance, like cosmic rubber bands that never snap. The philosophical stakes are just as profound. If matter is infinitely divisible, does reality have a basement level, or does it turtles all the way down into ever smaller layers? Prion theory bets on a deeper floor, but even it might just be a stepping stone. And if we one day crack open a quark to find prions, who's to say they aren't made of something smaller still? The journey inward could be as endless as the cosmos outward, a fractal cascade of complexity that redefines fundamental with every breakthrough. Now, let's pivot from the infinitesimally small to the astronomically vast. If prions hint at reality's hidden depths, the next theory challenges the immutability of the cosmos itself, suggesting the very laws of physics might be evolving. The universe's constants aren't just numbers, they're cosmic knobs, each twisted to an almost impossible precision. If gravity were slightly stronger, stars would burn out too fast for life to emerge. If the electromagnetic force were weaker, atoms couldn't bond into molecules. Even the tiniest tweak to these values would render the cosmos sterile, a vast graveyard of unformed possibilities. So why does our universe hit this infinitesimally narrow sweet spot? One radical answer lies in the anthropic principle, which flips the question on its head. We don't inhabit a universe fine-tuned for life because of luck. We exist because only a universe this precise could ever produce observers capable of asking the question. But that's just the starting point. Dive deeper, and you'll find theories that make the anthropic principle feel almost tame. Take Lee Smollen's cosmic natural selection, where universes evolve like biological species. In this daring model, black holes act as cosmic wombs, spawning new universes with slightly tweaked physical constants. Over countless generations, universes that produce more black holes, those with physics just right for stellar collapse, dominate the multiverse landscape. It's survival of the fittest on a grand scale, with our universe's life-friendly laws emerging not by design, but through a brutal Darwinian filter. Imagine a trillion failed universes, each collapsing into silence or flying apart too fast for structure to form, until one lineage stumbles upon the golden recipe. Then there's the variable constants hypothesis, where the so-called constants aren't fixed at all. What if gravity's strength or the speed of light have shifted imperceptibly over billions of years, converging toward values that permit complexity? Astronomers are already hunting for evidence in the light of distant quasars, probing whether the fine structure constant, a number governing electromagnetism, varies across space and time. If so, our universe's fine-tuning might not be a one-time miracle, but the end result of a slow, dynamic balancing act. Yet the most unsettling possibility is that we're seeing the fingerprints of something beyond physics. Theologians and some scientists alike have pondered whether fine-tuning implies a cosmic designer, though not necessarily in the traditional sense. Nobel laureate Freeman Dyson once mused that the universe must have known we were coming, while others suggest advanced civilizations could engineer universes in labs, tweaking parameters like programmers debugging a simulation. The truth might be stranger still. Perhaps fine-tuning isn't about life at all, but a side effect of deeper physics we've yet to uncover. string theory's landscape of possible universes, each with different constants, hints that our existence could be a statistical fluke in an infinite ensemble. Or maybe, as philosopher Nick Bostrom speculated, we're living in a simulation where the parameters were set deliberately. Whatever the answer, the fine-tuning problem remains one of science's most profound puzzles, a riddle written into the fabric of reality itself. And solving it might require not just new math, but a whole new way of seeing our place in the cosmos. Biocentrism turns the traditional view of reality on its head. What if the universe doesn't create life, but life creates the universe? At first glance, this sounds like philosophical musing, but scientist Robert Lanza grounds it in cutting-edge physics and biology. Picture a tree falling in an empty forest. Common sense says it makes sound waves whether anyone hears them or not. But biocentrism argues that without an observer, whether human, animal, or even a bacterium, the event isn't just unobserved, it's fundamentally undefined. The tree's collapse exists in a haze of quantum possibilities until consciousness crystallizes it into a concrete moment. This isn't just about perception. It's about the very fabric of existence being shaped by the act of observation. The roots of this idea dig deep into quantum mechanics. In the double-slit experiment, particles behave as waves when unobserved, spreading out in probabilities, but snap into definite positions the moment they're measured. Lanza takes this further, proposing that the observer effect isn't limited to lab experiments, it's the operating system of reality. Time, space, even the laws of physics might not be fixed features of the cosmos but emergent properties, like a movie resolving into focus only when a mind presses play. In this view, the Big Bang wasn't the beginning of everything. It was the beginning of a universe perceived, with its history coalescing as consciousness traces backward through the quantum fog. Critics dismiss biocentrism as a misinterpretation of quantum theory, arguing that observation in physics refers to interactions with any particle, not just conscious beings. Yet Lanza counters with biological fine-tuning. Life depends on absurdly precise constants. If gravity were slightly stronger, stars would burn too fast for planets to form. Biocentrism suggests this isn't coincidence. The universe isn't fine-tuned for life. It's fine-tuned by life, with conscious observation collapsing reality into the narrow configurations that allow its own existence. It's as if the cosmos is a grand cosmic choose-your-own-adventure book where the act of reading writes the story. Now imagine the implications. If consciousness shapes physics, could dying be less an end and more a transition, a shift in the observational frame that redefines reality itself? Near-death experiences, where people report vivid visions despite flatlined brain activity, might not be hallucinations but glimpses of existence beyond individual observation. Even the arrow of time could be an illusion, with past and future existing simultaneously until a mind imposes order. Biocentrism's boldest claim, the universe might be less a machine and more a living, evolving network of perceptions. But if consciousness is the architect of reality, where does that leave the cosmos when no one's looking? The next theory takes this puzzle deeper, suggesting that information, not matter or energy, might be the true currency of existence, with every particle, every force, just a bit in a cosmic code waiting to be read. Digital physics flips the script on reality itself. What if the universe isn't built from matter or energy, but from pure information? Imagine every particle, every force, even the fabric of spacetime as lines of code in a cosmic program, with the laws of physics acting as algorithms governing its behavior. This isn't just metaphor. Pioneers like John Wheeler, who coined the phrase "it from bit," argued that every physical event, from the spin of an electron to the birth of a star, might ultimately boil down to yes or no questions, binary choices etched into the foundation of existence. In this view, the cosmos isn't just described by math. It is math, a vast computational system where reality renders itself into being moment by moment. The evidence is more compelling than you might think. Take black holes, those cosmic shredders where gravity crushes matter into oblivion. According to quantum mechanics, the information swallowed by a black hole can't be destroyed. It has to go somewhere. But where? The holographic principle suggests it's smeared across the event horizon like data encoded on a celestial hard drive. If true, this implies that the three-dimensional universe we experience is just a projection of information stored on a two-dimensional boundary, like a movie playing on the surface of an immeasurably vast cosmic screen. Suddenly, the idea that reality is computational doesn't seem so far-fetched. But what's running the program? Some theorists propose the universe might be a self-contained computation, bootstrapping its own existence through recursive loops of information processing. Others speculate about layers beneath our reality, a motherboard of pure logic where the rules are written. There's even a wild hypothesis that quantum uncertainty, the randomness at the heart of particle behavior, could be the universe's way of generating new data on the fly, like a cosmic random number generator ensuring the program never gets stuck. The implications are staggering. If the universe is fundamentally informational, then everything from consciousness to dark energy might just be different expressions of data processing. Your thoughts could be algorithms running on the wetware of your brain, and the expansion of space might be the cosmic hard drive defragmenting itself. Even time's arrow, the relentless march from past to future, could be a side effect of information being processed in one direction, like a computer executing lines of code. Critics argue that calling the universe a computer is just poetry, a modern metaphor replacing older ones like the universe is a machine, but digital physics makes testable predictions. If spacetime has a finite information density, a smallest possible pixel size, then there should be a limit to how precisely we can measure anything. Experiments hunting for quantum foam, the supposed graininess of spacetime at the tiniest scales, might one day find evidence that reality is pixelated, a cosmic bitmap rendering itself into existence. Whether the universe is a simulation or something even stranger, a self-organizing network of pure information, digital physics forces us to confront a profound possibility. The bedrock of reality might not be rock at all, but data. And if that's true, the next question is even more extraordinary. Who, or what, is the programmer? Loop quantum gravity dares to reimagine the very fabric of spacetime, not as a smooth, continuous canvas, but as a shimmering tapestry woven from countless tiny loops, each a billion trillion times smaller than an atom. Picture the universe as an intricate mesh of interconnected threads, vibrating and twisting to create the illusion of three-dimensional space and the flow of time. This radical framework, born from the marriage of quantum mechanics and Einstein's general relativity, offers a breathtaking escape from the infinities that plague conventional physics, like the crushing singularity at the heart of black holes, where density becomes infinite and equations break down. In loop quantum gravity, there's no such thing as infinite density because spacetime itself has a smallest possible stitch in its cosmic quilt. The magic lies in the loop's behavior. Unlike string theory's vibrating filaments floating in higher dimensions, these loops are spacetime's fundamental building blocks, linking together to form networks called spin foams. When you move your hand through the air, you're not gliding through emptiness, you're navigating a dynamic web of these loops, rearranging themselves like a cosmic game of cat's cradle. This pixelation of reality isn't just theoretical. It could explain why black holes don't crush matter into oblivion. Instead, at their cores, the loops reach maximum density and rebound, transforming the singularity into a bridge to another region of spacetime, a cosmic bounce that could birth new universes. But how do we test such an abstract idea? The universe might be leaving clues in the oldest light we can see, the cosmic microwave background. If spacetime is granular, light traveling across the cosmos for billions of years should subtly scatter, like a marble rolling over a bumpy surface. Astronomers are hunting for these tiny fingerprints in the microwave glow, while others probe the fabric of reality using ultra-precise atomic clocks. Even gravitational waves could carry whispers of loop. Quantum gravity's affects ripples in spacetime might behave differently when passing through this quantum weave, like sound waves warping as they travel through a forest. The implications stretch beyond black holes. If spacetime is woven from loops, then the Big Bang wasn't a singularity. It was a big bounce, the explosive rebound of a previous universe that collapsed to its smallest possible size before springing back outward. Time itself might not be fundamental but emergent, like the melody arising from the notes of a song. And if the loop's vibrations can be harnessed, we might one day manipulate spacetime itself, engineering wormholes or crafting quantum engines that bend the rules of physics. Yet the most profound revelation could be philosophical. If reality is pixelated, then continuity, the smooth flow of time and space we take for granted, is an illusion, a cosmic sleight of hand performed by the universe's underlying code. The next theory doesn't just challenge our perception of reality, it asks whether nothingness itself might be a mirage, hiding untapped energy and structure in the void we call empty. Quantum foam isn't just a poetic metaphor, it's the turbulent underbelly of reality, where spacetime itself churns with unimaginable violence at scales a billion trillion times smaller than an atom. Picture the vacuum of space not as serene emptiness, but as a storm-tossed sea, its surface constantly boiling with pairs of virtual particles that blink into existence for mere instants before annihilating each other in bursts of raw energy. These aren't mere quantum hiccups, they're the universe's fundamental texture, a seething froth where tiny wormholes might spontaneously form and collapse, stitching spacetime into an ever-changing labyrinth. At this level, the very concepts of here and now lose meaning, distances fluctuate, time stutters, and the geometry of reality resembles the chaotic spray of an ocean wave frozen mid-crash. This frenzy isn't just theoretical noise. Quantum foam could solve two of physics' deepest puzzles. First, consider black hole entropy, the baffling discovery that these cosmic vacuums possess an intrinsic disorder proportional to their surface area. Where does this complexity come from? The answer might lie in the foam's chaotic dance. As a black hole's event horizon stretches and contorts at the quantum scale, it could trap and stretch the frothing spacetime beneath, imprinting its turbulence like fingerprints on glass. Each microscopic wormhole fluctuation becomes a bit of information, a tiny scratch in the cosmic record explaining why black holes aren't the simple pits we once imagined, but the most complex objects in existence. Second, the foam might explain why empty space crackles with zero-point energy, the faint but measurable hum of quantum fluctuations that prevent atoms from ever truly resting. Imagine dipping a thimble into this quantum sea. Even that tiny volume would contain enough seething energy to boil every ocean on Earth. The catch, most of this energy cancels out instantly, leaving only faint ripples we can detect through effects like the Casimir force, where uncharged metal plates in a vacuum inexplicably pull together, squeezed by the foam's relentless pressure. But here's where it gets truly bizarre. If spacetime is this unstable at microscopic scales, what stops the entire universe from tearing itself apart? The answer might lie in the foam's self-regulating nature. Just as turbulent ocean waves average out to a calm surface when viewed from afar, quantum chaos could smooth into the orderly spacetime we experience, a cosmic illusion created by our macroscopic perspective. Some theories even suggest that dark energy's repulsive force, accelerating the universe's expansion, might be the cumulative sigh of this restless quantum sea, its infinite tiny fluctuations adding up to push galaxies apart. Yet the most tantalizing possibility is that the foam isn't just background noise, but the substrate of reality itself. String theorists propose that what we perceive as particles might actually be vibrations of microscopic strings whose harmonies are distorted by the foam's churn, like a melody played on a warped guitar. Loop quantum gravity takes this further, suggesting spacetime isn't continuous but woven from discrete loops, meaning the foam's turbulence might literally be the threads of reality twisting and knotting. The challenge, observing this pandemonium directly, would require probing distances so tiny they make quarks look like planets, but ingenious experiments are hunting for footprints. Some telescopes search for gamma rays whose wavelengths might get chopped up by the foam's texture as they travel cosmic distances, like light shimmering through heat waves. Others propose using entangled particles to detect if spacetime's graininess disrupts quantum correlations. Each test brings us closer to answering whether the universe's calm facade hides a quantum maelstrom, and whether that chaos might hold the keys to uniting gravity with quantum mechanics. Now, listen closely. If spacetime truly froths at these scales, then every quiet moment of your life, every still night under the stars, is an illusion woven from unimaginable turmoil. The chair you sit on, the air you breathe, even the neurons firing in your brain all rest upon this seething quantum ocean. And if we ever learn to navigate its currents, we might discover that reality is far wilder, far more dynamic than our senses could ever perceive. This brings us to the next cosmic whisper, the possibility that the universe isn't just turbulent, but echoing. Across unimaginable distances and timescales, patterns might repeat, shadows of ancient events reappearing like ripples bouncing off the edges of reality. Eternal inflation paints a picture of the cosmos not as a single, isolated event, but as an endless fireworks display, each spark a newborn universe bursting into existence within an ever-expanding void. Imagine a pot of water boiling relentlessly, with bubbles forming, rising, and popping at the surface. Now scale that up to cosmic proportions. Our universe might be just one bubble among countless others, each with its own unique physics, stars, and perhaps even life, all floating in an infinite sea of inflating spacetime. This isn't just a metaphor, it's a serious scientific framework that could explain why our universe looks the way it does, and why others might look radically different. The theory builds on Alan Gough's groundbreaking idea of cosmic inflation, which proposes that the early universe underwent a mind-boggling exponential expansion, smoothing out wrinkles and setting the stage for galaxies to form. But eternal inflation takes this further. What if inflation never truly stopped? Instead, it continues eternally in the background, with pockets of spacetime randomly relaxing into stable universes like ours. These bubbles nucleate like droplets in a mist, each one a self-contained cosmos with its own laws of physics, separated by an ever-stretching ocean of hyper-expanding space. Some bubbles might have stronger gravity, making stars burn out in seconds. Others could lack electromagnetism, preventing atoms from ever forming. The diversity is staggering, limited only by the possible combinations of fundamental constants. Here's where it gets even wilder. The multiverse's infinite variety might solve one of cosmology's biggest head-scratchers. why our universe seems so finely tuned for life. If every possible physics plays out somewhere, it's no surprise we find ourselves in a bubble where the numbers align just right for galaxies, planets, and thinkers like us. This anthropic selection isn't luck, it's statistics on a cosmic scale, and the uniformity of the cosmic microwave background, that ancient glow from the Big Bang. It's not a mystery if our bubble was once a tiny patch of inflating space stretched to astronomical smoothness before the transition. But how could we ever test such a mind-bending idea? Clues might lie in the faint imprints left on the cosmic microwave background. If our bubble universe collided with another in the distant past, the gravitational shockwaves could have left scars, subtle circular patterns in the sky. Telescopes like Planck have hunted for these bruises, and while nothing definitive has been found, the search continues. Another approach probes the universe's curvature. Eternal inflation predicts our bubble should be perfectly flat, a prediction that aligns eerily well with observations. The implications ripple beyond cosmology. If eternal inflation is true, the multiverse isn't just a collection of universes, it's a living, breathing ecosystem, constantly giving birth to new realities. Some might flicker out instantly, collapsing under their own unstable physics. Others could harbor civilizations far older than ours, their skies filled with the light of alien suns. And somewhere out there in the froth, another bubble might be identical to ours in every way except for the outcome of a single quantum event, creating a parallel world where every choice branches into infinity. Now consider this: if the multiverse is eternal, has it always existed, or did it too have a beginning? The next theory doesn't just explore the birth of universes, it suggests time itself might be an illusion, a side effect of a deeper, timeless reality where past, present, and future exist simultaneously. Grand unified theory isn't just a scientific goal, it's the ultimate cosmic jigsaw puzzle, where four seemingly unrelated forces must snap together into a single, elegant equation. Picture the universe as a symphony with electromagnetism, the strong and weak nuclear forces, and gravity, each playing their own instruments, following different sheet music. The dream, to find the maestro's score that unites them all into one harmonious composition. For decades, physicists have chased this holy grail, knowing that if they succeed, it would reveal reality's deepest blueprint. A set of rules so fundamental they could explain everything from the spin of an electron to the whirl of galaxies. So why is this so hard? The forces don't play nice. Electromagnetism and the nuclear forces have been partially unified under the Standard Model, which describes them as different vibrations of underlying quantum fields. But gravity, Einstein's warping of spacetime, refuses to join the party. At the quantum scale, gravity becomes a cacophony of infinite probabilities, while the other forces hum along with precision. It's like trying to merge the rules of chess with the chaos of a hurricane. The math simply breaks down. Enter string theory, one of the most promising contenders. Imagine if every particle isn't a dot but a tiny, vibrating string with different notes corresponding to different forces. In this symphony, gravity's dissonance might just be a vibration we haven't learned to hear yet. String theory's elegance lies in its ambition. It doesn't just unify the forces, it suggests they're all facets of a single, deeper structure woven through higher dimensions. But there's a catch. To make the equations work, strings require 10 or 11 dimensions, most curled up so tightly we'll never perceive them. Testing this isn't just difficult, it might require energies approaching those of the Big Bang itself. Loop quantum gravity takes a different path, treating spacetime as a fabric woven from microscopic loops. Here, gravity emerges naturally from the quantum tangles, like waves rising from the ocean's surface. The beauty, no extra dimensions needed. but the trade-off is a universe where time and space are pixelated, a digital cosmos that might clash with the smooth continuity we observe. The stakes couldn't be higher. A successful grand unified theory wouldn't just fill textbooks, it could unlock technologies straight from science fiction. Imagine controlling gravity as effortlessly as we harness electricity, or tapping into the quantum vacuum's energy. But beyond practicality, it would answer existential questions. Was the universe inevitable, or are we living in one fragile version of countless possibilities? Does reality have a single set of rules, or is physics itself a cosmic accident? Yet even if we find this equation, the next question looms: what lies beneath it? A theory of everything might not be the end, but a doorway to an even deeper mystery, one where the universe's code is written not in forces or particles, but in something far stranger. Boltzmann Brains take the concept of cosmic randomness to its absolute extreme. What if your thoughts, memories, and even this very moment aren't the product of billions of years of evolution, but a fleeting glitch in the void? Picture a single, self-aware consciousness spontaneously assembling from quantum chaos, complete with false memories of a past that never existed, convinced it's a real person in a real universe. According to this unsettling thought experiment, in an infinite cosmos governed by entropy, such phantom minds should arise far more frequently than actual flesh and blood beings like us. The math is chilling. Over unfathomable timescales, random fluctuations could construct a disembodied brain down to the last neuron, hallucinating an entire reality, only to dissolve back into the noise an instant later. Statistically speaking, in an eternal, chaotic universe, Boltzmann brains, named after physicist Ludwig Boltzmann, should outnumber ordinary observers like grains of sand dwarfing planets. So here's the existential gut punch. How do you know you're not one of them? This isn't just philosophical paranoia. The paradox emerges from thermodynamics, the science of heat and disorder. In any system, entropy, a measure of chaos, tends to increase over time, but occasionally, purely by chance, molecules can arrange themselves into orderly patterns. In a vast enough universe, given enough time, even the most improbable events become inevitable. A hurricane assembling a Boeing 747 from scrap metal. Statistically possible. A fully formed mind popping into existence from quantum static. According to the numbers, it's not just possible, it's practically guaranteed. The problem arises when we apply this logic to our own existence. If Boltzmann brains are more probable than evolved beings, then the odds suggest you're far more likely to be a momentary fluctuation than a product of Darwinian selection. Yet the theory self-destructs in a spectacular way. If most observers are Boltzmann brains hallucinating coherent realities, then their observations of the universe, including the laws of physics we've painstakingly deduced, are meaningless illusions. But here's the twist: our scientific models work astonishingly well. We've predicted particles, engineered technologies, and landed probes on comets using math rooted in a universe that behaves consistently. If we were Boltzmann brains, the likelihood of hallucinating a cosmos with such precise, testable rules is vanishingly small. This inconsistency leads many physicists to reject the idea, arguing that any cosmology predicting we're probably delusions must be flawed. The debate forces us to confront the nature of reality itself. Some theorists propose escape clauses. Perhaps the universe isn't infinite, cutting off the time available for freak fluctuations. Others suggest consciousness can't arise from random chance alone, requiring the scaffolding of a real, evolved brain. But the most intriguing resolution might lie in quantum mechanics. If observation plays an active role in shaping reality, As some interpretations suggest, then Boltzmann brains couldn't sustain a consistent universe because they're not truly observing anything. They're cosmic mirages flickering in and out too quickly to stabilize the world around them. Ultimately, the Boltzmann brain paradox isn't just about us. It's a stress test for our theories of the cosmos, exposing the cracks in our understanding of time, entropy, and existence. While we're almost certainly not Boltzmann brains, the fact that the question even arises reveals how little we grasp about the universe's true nature. And if nothing else, it's a humbling reminder, in an infinite cosmos, even the impossible might be waiting its turn. From holographic realities to quantum consciousness, each of these 30 theories isn't just a flight of fancy. They're the cutting edge of human curiosity, daring to rewrite the rules of reality itself. Think about that for a moment. The cosmos we thought we knew, with its neat laws and predictable motions, might be nothing more than a facade, a thin veil over something far more intricate and mysterious. Whether it's the holographic principle suggesting our universe is a cosmic projection, or the spine-tingling possibility that consciousness could be woven into the fabric of space-time, these ideas don't just challenge science, they redefine what it means to exist. Consider the implications. If even one of these theories proves true, the ripple effects would touch everything. Black holes could become gateways, not graves. Dark matter might be the gravitational echo of a parallel universe brushing against ours. Time itself, that unshakable arrow, could be an illusion, a side effect of deeper quantum processes we've yet to uncover. It's humbling and exhilarating all at once, a reminder that the universe isn't just stranger than we imagine, but stranger than we can imagine. And here's the beautiful part. This isn't just for physicists in ivory towers. These theories belong to anyone who's ever looked up at the night sky and wondered what if. That's why we've explored them together, to spark that sense of awe, to remind you that the cosmos is a story still being written, and we're all part of it. So, which theory grabbed you? The mind-bending multiverse, where every choice spawns a new reality, or the eerie elegance of cosmic natural selection, with black holes birthing new universes like cosmic seeds? Drop your thoughts in the comments below. Let's keep this conversation as boundless as the ideas we've explored. If today's journey through the universe's wildest possibilities left you hungry for more, hit that subscribe button and ring the bell. Because this is just the beginning. From the quantum foam beneath our feet to the holographic edges of reality, there's always another mystery waiting, another door to pry open. Thanks for joining me on this ride through the cosmos' deepest enigmas. Until next time, keep looking up, keep questioning, and never stop marveling at the fact that we get to unravel these wonders together. The universe is calling. Let's see where it takes us